Hello everybody, welcome back to another edition of the Modicon M221. I'm your host, Leandro Mada, and in this video what we're going to see is a small introduction to control systems. The idea of this module is to talk about the PIDs, but before starting with the PIDs, I believe it's going to have an idea of how to control a system, or what a system is, and the different ways that we have to control something. Okay, so let's go to the presentation. So just in order to start with in order to understand the PIDs, it's important to know the location. It is important also to know the different systems that we have. Okay, so we have the process, we have inputs and outputs. The idea of this PID that we're going to see on the controls or different kind of controls is related to SISO, single input and single output of the process. So we have one input and we're going to have one result, the output. That is this kind of process that we have. Okay, you can see later in different books that you can have SISO, MIMO, or a combination of both. But in this case, we're going to focus only single input and single output systems. So we have our process, okay, the thing that we want to control. Okay, so we have two main kind of control system. We have the open loop, so we have the controller, we assign one actuator. Okay, it's not a physical actuator, it could be something that sends the value to what we want to control. Okay, and we don't have any feedback. Okay, that's actually the open loop system. And then we have the closed loop. So we see the loop. Let me just hide myself. Okay, so we have the complete system where we have the for example this. So we have the desired output that we want here, and for the process to be activated, and then we have something to have a feedback. Okay, so for example, if you want just a motor to run, okay, it doesn't matter the velocity, you can define an open loop. So just open the motor, just go to one specific velocity, it doesn't matter, just run it. Okay, for example, using a soft starter, we go to 50 Hertz, and that's it, open loop. We just know it's going to work. But if you want, for example, more precise control, you can use, for example, a sensor to measure the unit or the variable that you want for the process in order to compare that value, okay, with the desired output. That's going to be your set point. Okay, and then with the controller, you can define how you're going to control the process that you want. Okay, the important thing here, as you can see, okay, is that you need to compare the same units. For example, if you're gonna have some kind of comparison to execute and change the value that you have in the process, you will need to define first the right sensor, so you can have a feedback, and then with that feedback that you have, change or convert the value to compare with the set point that you have. Otherwise, if you are comparing apples with pears, it doesn't make any sense for your control. That's why it's important to select the right type of sensor and also make the right comparison on the controller. Okay, now saying this, we continue with this part. Okay, good. So my focus here in this basic control system that I'm going to explain now is to focus on the closed loop systems. So let me just move myself. There we go. So this is what we got. Okay, so let me just hide. There we go. This is what we have for the closed loop. Okay, so if we pay attention in here, okay, this can be our controller. Okay, let me just put the pen. This part over here is going to be our controller. Okay, that can define the type of logic that we want. Okay, and here there's some examples on PLCs. Okay, M221, M241, M251, M262, Modicon M172, M71, 72. You can also use a Celia or another EPAC or a pack controller, it doesn't matter. Any controller will do something like this, that you can make the comparison of your logic of the variables that you have based on the set point and the actual value, and then you create your logic, and the logic will be located on the controller side. Okay, now sometimes you will need to configure this set point. Okay, so you can have a HMI, okay, in order to change those values of the same point, and probably make some additional modification to in some parameters in the logic that you're going to have in order to control the process. Okay, so as feedback, okay, you will need to select the right type of sensor that you have. Okay, so you have pressures, you have humidity sensor, temperature. Okay, you can have also to measure the flow. There is a lot of type of sensor, but you need to specify which should be the variable that you're going to have over here that's going to be affected. Select the right kind of sensor so you can get the value over here, and then you can compare it with the set point that you're going to have. Okay, that's basically the idea. Okay, we are not talking right now about the PID or different kind of control. It's not the idea, it's just to have a concept of what's going to do this kind of control. Okay, the idea is to know the control systems here and then how the real impact of the PID. So if we continue with this, okay, let's imagine now that we have a temperature control, okay, for house. So the idea of the control on-off control is to have like a digital output, okay, that's going to be on or off depending on the value that you have or in the logic, based on the comparison on two variables. That the variable here is going to be the temperature, for example, in the room. Okay, so the set point is going to be a temperature. Okay, and the process variable is going to be the feedback that I have in the loop in order to control. It's going to be temperature also. So here you will need to select a thermocouple or another kind of temperature sensor to read the value, the actual value that you have in the room. And then in the controller, you can create some kind of logic, okay, in order to activate on and off the value, one of the outputs. And then, for example, you can use a heater, and you can use, for example, a solid state relay in order to make the actuator to use in the with the heater, okay, and then you can control the temperature you have in the room. Okay, so that's could be one of the process. As you can see over here, this basic control on off, okay, depend on the value that you have with the set point and the process variable that you have, process value variable that you have, it will activate the output. So you can see here, imagine that you are controlling the temperature. If the temperature is lower than the set point that you have defined, okay, for example, if you want the set point temperature be 22 degrees, okay, here you can see that the process variable is below, let's say 20. So it will start rising because the comparison says that the process value is lower, so it will increase because I inactivated the output until it reached the set point. Okay, once it reaches the set point, it will be off. As soon as the process variable down, okay, the temperature is down, it will activate again, and so on and so on and so on. So this is just one way to see this, but this can also apply to different kind of system where you just have like a small comparison and have a on-off control. Okay, for example, here you can use more advanced control because, for example, here you're just using a heater, using a solid state relay or other kind of contactor or relay that you have, and it will activate the output. But imagine now that you are not going to, you imagine that you're going to control a valve or using a motor in order to a pump, or you're using a huge motor. If you're trying to activate a comparison and you don't have like some kind of hysteresis or deadband, okay, the amount of energy in each start is going to be huge. and probably it's not going to be the right effect in the installation or in the plant about the behavior. So that's why it's probably you have some kind of hysteresis of that band just to reduce that using this kind of control, as you can see over here. Okay, in this case, there is no only the actuator is not only the relay. You can use actuator, okay, for example, for a valve, or you can use a starter, okay, in order to turn on a motor or a valve or whatever you want. Okay, it would depend on the process that you have. So to this side point that we have, we can use a deadband or hysteresis. I'm using here hysteresis. So basically the hysteresis is in one way on the control that we have, okay, here in the previous one, okay, the on off. The direction of the control is the same, okay, but in this one the direction is different. So it goes in one way when it's rising, but when, for example, when it's decreasing the temperature, okay, it goes in another direction to make the control. Okay, so basically that's the idea. And a deadband is just have a gap where the value is 0 at the end. So basically that's the rough idea. So as you can see over here, I have like a gap, and I give more space between the turn off and turn on of the actuator. But this can be used in a different kind of applications, okay, not only for temperature, but you can have it. And if you take a look, if you reduce this hysteresis to 0, okay, it will be the same as you have over here. So this is just a standard on-off control. So if we take this on-off control into a PLC, okay, for example, the M221, let's just put the complete view. Just bear with me. Okay, so now there we go. So this is just a template, or how you can use a cooling system, for example, for the on-off with hysteresis. So basically this is the logic. So I have an enable on the control, as you can see over here, and depend on the comparison between the process variable and the set point, okay, it will activate the output or not. Okay, as you can see over here, let's start with the temperature 28.3. okay, so here at the moment is off, okay, this is off, and this is the enable, okay, and this is the output Q. So as soon as the enable is 0, there is no control, nothing at all. But as soon as I press this one in true, okay, for cooling, you can see that the temperature we should reduce until it reaches the value is required. So here you can see here it will start decreasing the temperature, okay, until the temperature, okay, this is the temperature, reaches the value of the, here is the just have a check, this is the set point, and this is the set point, this is the set point, okay, set point, and this one is the set point plus the hysteresis, okay. So here it will reduce up to this point, so the temperature will start increasing, but in this point where the set point is different, the temperature and the set point is the same, it's not activated because I have this hysteresis. So as soon as the temperature reaches the set point plus the hysteresis, okay, it will start on again. Okay, so that's basically the idea of this kind of control, and the same can be applied, for example, instead of cooling, for the heating. Okay, this is just a quick example how you can do it. Okay, so I have this is the same, this one is the enable, this one is the output, okay, for the heating. As you can see, it starts with low temperature, okay, it reach in this part, it reaches the set point, minus the hysteresis. Okay, and this one is the set point. So here you can see, even if we reach that, it doesn't turn off the heater. Okay, it waits until it reaches the set point. So if you follow the line, it just go over there. Okay, it just go to 0, and then when it's over here, okay, when it's reached the set point, oops, it doesn't go up, okay, because I had hysteresis, and it will turn on when the temperature decreases to the set point minus the hysteresis. So this gives us, okay, a gap. Imagine if you don't have hysteresis, if you have a normal relay, it's gonna be like, it's gonna turn on constantly, on and off constantly. You will hear the relay because we don't have this hysteresis. And if you extrapolate this to another kind of machine or kind of plant where you have a huge motor or a huge device that have too much consumption, you can see that the behavior is not going to be good if we turn off and off constantly. So for that reason and another ones, okay, that's why we start using some kind of different kind of control where the output can be variable. Okay, so we have, for example, if we use a digital output, okay, we can use a PWM system. So in this case, the heater is going to be the same, but we can change how we're going to heat the room, okay? Or we can use the analog signal to control a drive, okay, just to indicate how it's going to be the velocity of the motor that we're going to have. Or we can change the actuator. We can, the physical actuator, we can select the actual position of the valve, okay, for the air to flow or the liquid or whatever we have, okay. So that can be managed not by the on-off control, okay. The idea here is to use the PID control, okay. So the first part about the different kind of control system is to have an idea what we're going to, or how we are going to use the PID, okay, just to have an idea that we're going to close the loop, okay, and in order to identify the elements of the system. So the idea of this PID is to have the logic of the controller, okay, just to have a precise control. But this precision that we want of the control will depend on some parameters that we have on this PID that we're going to cover. So you can see in this picture, okay, we have the same part, the actuator, but it only can change some of the device that we're going to use in order to control the process, okay. Here in this part, we can see that inside the controller, or despite the controller, we're going to have the PID. If we focus on the controller side, on the PLC, okay, we normally use some kind of function block, and in the function block, we just need to enter the set point, which is the actual value, and some additional values related to the PID, okay. So this PID, it comes on 3 parts, okay, 3 different components that allow us to change the behavior that we're going to have here in the output, okay. But the value that we are going to have on the PID will affect how we're going to make this actuator works to have the right response on the process, to have the right value that we want in the set point. So this PID is based in 3 kind of components. We have the P for proportional, I for integral, and D for derivative. Each of these parts of the PID have a fundamental role. So let's start with the proportional first. The proportional basically creates proportional signal, okay, based on the error that we have. Okay, so as you can see here at the bottom, we have the set point and we have the process variable. Okay, as you can see here at the bottom, we have a minus sign. So what the PID does is to check, okay, how far from the desired value that we want, which is the set point. So it creates this kind of error, okay, that basically subtracts from the set point to the set point instruction of the process variable. That gave us an error. Based on that error, each part of the PID has an influence. So for the proportional part, it creates a proportional value based on this kind of error. So the closer we are for this set point, okay, the lower will be the action, because the proportional part is gonna have less interaction or less component in here. Okay, so imagine that let's try to see if I have like this. Okay, so this is gonna be the set point. Okay, and if we are using this kind of only proportional part, okay, we're gonna have the error. Okay, here the error is gonna be, let's try to do it in the different way. Just try to quick and fast doing this. So this is a set point, and here you should be able to see this value, okay, going to be decreasing, okay, and it can have like a constant error. Okay, this one's going to be the error, which is this value minus this one, which is the process variable. So you cannot see it. There we go. So you can see the error probably, if we don't, with this proportional, okay, the influence of the proportional will be less and less until I how can I explain this part? Okay, so we have the process value, okay, and the set point that we have. This gives us an error. Okay, so as soon as the error starts reducing, because the error is affected by the proportional part that sometimes we call and use KP for proportional constant, the proportional constant. Okay, this the influence of this combination during time, okay, will be less and less, okay, because the error will be decreasing, okay, as you can see over here. This one and in the stationary state can give us a constant error, okay. So that is the effect of the proportional part, okay. I don't want to get into the mathematical part, because that would be just a complete class and it's not the idea. So that's basically what the proportional does, okay. So you have an error, and the value that you put in there will give us a proportional component based on that error that you have. And then in order to avoid that stationary state that we have, okay, this error that we have, okay, in the stationary state, in order to reduce that to 0, which is what we want to have the desired value, is to add this integral part. So this integral part that we have, it can be the KI, or sometimes it's called TI. It will depend on the control load that we have inside this PID, okay, because it can vary, it can be different depending on the control that we use. Okay, let me just okay, like this. So it will generate let's see, this integral component, okay, will have a relationship between the error that we have in the stationary state and the magnitude that we have, okay, the magnitude and the duration that we have for this error that we have. Okay, so based in the duration of the error that we have between our desired value and the process value and the duration of that, okay, the integral part will have an effect in our global value that we're going to have over here. Okay, that is the idea. Okay, the idea is to reduce the error that we have. Okay, and then the derivative part that we have, if you want to say in a way, it's not like a prediction because we have a different kind of control, a predictive control for this, but it's like it sees in the future, okay, on the changes that we may have. I think I wrote it down this. Okay, see, yeah. This component sees what the error will be in the future. Okay, so basically that's the idea. So depending of how the error changes, how it fluctuates, the derivative component will be stronger or not. Okay, so basically that's the idea. So to sum up, we have the three components in the PID. That's why we call PID. The proportional we only see it will affect, or the influence of the proportional part will be based on the signal error that we have. Okay, and then the integral part will be related to the error that we have on the stationary and the duration that we have of that error, and the derivative is how it changed this error. Okay, so that's basically the idea, or what I want you to know, okay, for this. And based on this combination of values, okay, we can have, or in ideal case, we can have these three behaviors or waveforms from our desired output. Okay, so we have the first one, which is the critical dump or normal behavior, as you can see. So this is the set point and this is the process value. I have already configured all the values of the PID. So it reaches, it can go there and it just stay in there, which is the ideal situation. Okay, this definition, I get it from this site. Okay, I believe it's gonna be good if you take a look. And then we have the overdump, which in Spanish is gonna be the sobreamortiguado. That basically, you can see here the behavior. We got the set point and we don't have any overshoot. Okay, we don't have this part. This is the overshoot. We don't have this part. We don't have it. That's why it's go under the set point. Okay, and depend, for example, on the value of the integral part, this error can be like this. Okay, like this, and you have the error on the stationary that it will be affected by the integral part. And then we have the underdump, okay, which is this one, okay, which is sobreamortiguado, no, subamortiguado, okay. In Spanish is subamortiguado, sistema subamortiguado. In English is underdamped. That basically, you can see here, it's totally different to the other one. Okay, you can see that it starts going around the set point that I have selected. Okay, and this will depend also on the parameters that we have configured in the past. Okay, we can have more overshooting, okay, and it will reduce, okay, like this, and reaching the set point. Okay, so basically that's the idea of different behaviors that we can have. Now, these are some ideal scenarios. If we, for example, don't configure properly the PID, okay, this, just hold on a minute, we may probably have, instead of this, something like goes to the max point, like this, and it goes to the oscillation. Okay, so if it goes like this, it's not good. Okay, there's something wrong over there. But sometimes, okay, not sometimes, no, in the theoretical part. If you reach this point, this will help you to know some parameters of how to calculate the values for the PIDs. Okay, so saying that, okay, I don't want to enter into the mathematical details because that is another topic I don't want to touch right now. It's just a quick introduction, basic introduction about control systems. So as you can see here in the left part is a PID block, how it could be the logic inside one controller. And on the right part, here on the screen, you can see another PID. So here we need to be careful. You can say, okay, I have this system working in a PLC brand A, but when I use those values in the PLC B, it doesn't work. Okay, what we need to check here is that the control law inside the controller, they probably are not the same, they are different. Okay, that's why you need to be careful here. As you can see over here, you have the component P, the component I, and the component D. Okay, they're really added and then we get the value for the actuator that we have. Okay, here the integrated part and the derivative part are added, and then everything is multiplied by the proportional part. Okay, which is totally different to what we have over here. Okay, it's different. So that's why we need to be careful. Probably we try to use the value that we have in one PLC, one brand, and trying to use in another one, and it doesn't work. And this can maybe be the reason. Okay, so we need to be careful here. Okay, as you can see here at the bottom, you can see too much mathematical stuff, but I'm going to get into details, at least now, I guess. So this is it, more or less, of the PID. What we have, for example, in the Machine Expert Basic for the Modicon M221 is the possibility to use the auto tuning. So the auto tuning, we're going to cover that later. It will go through different values for a few cycles in order to calculate these values for the KP, or sometimes called TI or KI, or sometimes also call it KD for the derivative part, KD or TD. Okay, in order to calculate these constants or times in order to get the right values of the PID. Okay, we got this auto tuning in the Modicon M221 and also in the M17.2 and 71 for the HVAC offer. Now, this is some of the books that I use in the university and when I study control systems and advanced control also. So we got, in case you want to go further with this, you have from the Ogata, which is the modern control engineering, and then we have the modern control system by Bishop and Dorf, and then another one which is the Kuo from the book called Automatic Control System. These are the three books that I believe they're good to have more knowledge about the control, just to get a few more ideas, a lot more few about this. And I also found two videos on YouTube, one from MATLAB and then from another company explaining the PIDs. I believe have a good introduction. But what I wanted to do in here is to give you flash idea about the different kind of system and how we can differentiate here, and we're going to focus only in the closed loop so we have more control in what we're going to do. Okay, as you can see over here, we have the feedback. So when we have the feedback, we should be able to control, or ideally try to control, what we want in the process. Then we need to define which is the right sensor. The sensor is going to be critical here if we want to make a control. If we don't have the right sensor, there's nothing we can do actually. That's why the variable that we want to measure needs to be measurable. Otherwise, there's nothing we can control. But for that, you have predicted control also. But this is just a quick idea. So we have also the controller now for basics application, as I show you the temperature control. I have the example of this, so I can also share it. And the PID, the idea of this module is to focus on the PID. So later we're going to see how we can configure the PID blocks in the, when I put this, how we can configure the PID blocks, or have an idea how to configure the PID blocks, how to auto-tune in on the M221. So I believe this is it, just to have a rough idea of the control systems. Okay, I didn't involve too much on the PID explanation, okay, because it's not idea. I don't want you to be an expert on the PID, on the control engineering. I don't want that. I just want you to know that you realize, okay, this is for proportional, what can done, just to have an idea that you are touching something in the controller that's going to affect the output, okay, but just want to have a rough idea how it can affect the output. Okay, so thank you very much for watching this video, and I see you on the next one.